And so I'm going to talk about implicit differentiation, which basically, to sum this up, is you're going to do what we've been doing, but there might be x's and y's in your function, in your equation. So up to now, it's been everything like this, either y or f of x equals something just with x in it. Okay. And now you can see some examples below here of like, all right, there's going to be x's and y's and y squared, y cubed in there. You might say, why would we need that? Well, there's other types of equations that have y squareds and other things. So I'll give you an example of that at the bottom of the page. And okay, the word implicit. So I gave you a contrast here. Explicitly defined functions are able to be solved for one variable. Everything we've been doing so far, they're already solved for y. This one's already solved for one variable x. This one right here, it's not, but it could be. So that's what it means explicitly defined. You could solve it, it could just be one variable, like solve for one variable, y equals something, x equals something. Implicit, so the title of this section, it's not able to be solved in terms of one variable. So we wouldn't be able to get it like this anyways. So here's some examples. You would not be able to solve for just x or just y. Okay? So that's what we're doing. What if, and it works both ways, this process, so if it's explicitly or implicitly defined. But it's mainly helpful for this type. Okay, so let's go down. So here's the process. There's not a ton new. There's only one little step that's going to be new. To differentiate, we'll treat one variable, usually y, as a differentiable function of x. And just to differentiate both sides of the equation. So I relate it to like, I don't know, like this. It's just kind of like you're doing like square root of both sides of the equation. Well, I'm doing the derivative of both sides of the equation. Kind of that same thing. I'm multiplying both sides of the equation. Okay, I'm going to do the derivative of both sides of the equation since I can't really solve for x or y. Let's see, what else do I say here? So then what we're going to do is we're going to get a dy dx. Now, I want you to get used to this. These mean the same thing. Y prime is the derivative of y. Same as dy dx. This one is a little more helpful, though, because it tells us what variable we're doing a derivative in respect to. So maybe if I did that, that would say the derivative of y with respect to the z variable. If all of these were like z's or something. That's why that one's a little more descriptive, and so we use that one a little more often. Okay, but they mean the same thing. Okay, that's basically it. I'm going to show you how to do it, the process, and then I sum it up on the next page, like what I've been doing. I think I'd like to actually just go right to this example here. Okay, so find dy dx given y squared equals x. Now I know what you're saying. Couldn't we actually solve this one for y by doing the square root of both sides? Mm-hmm. Yeah, we could. And then we know how to do the derivative of this. Change it to a half power. Yes, you could. I'm just going to show you the process doing it implicitly. So here's what you do. I'm just going to rewrite y squared equals x so I have a little more room here. What I'm going to do is I'm doing the derivative of both sides of the equation. I really do that like on this one. I'm really doing the derivative of this side as y prime. The derivative of this, I do the power rule. Okay, it's just going to look a little different though here. So I'm doing the derivative of both sides, which I've really done with this. I'm really doing, okay, what's the derivative here? It's y prime. And then here we do the power rule. Okay, so I'm going to be writing d dx. That means the derivative, d, with respect to the x variable. So basically I'm doing like I'm squaring both sides or multiplying both sides. I'm doing a derivative of both sides. Okay, so here's what we do. Now, let me go ahead and do the right side. It's 1, right? Derivative of x1. Got that. I'm going to do the derivative of this one. Here's the issue. I want it in respect to the x variable. So what I'm going to do, it's not an x variable. What I'm going to do is normal rules. Right? I do the power rule. 2 I'm applying really the chain rule here, so this is where talk through that. And in power rule overall, I bring down the 2, I subtract 1 to the first power. Then what do I do? This is my inside emoji. I keep the y. You might say normally what it would be 2y. Chain rule times the derivative of y, which is y prime or dy dx. So right there, you could write y prime or dy dx. I'm going to be writing y prime. Now, guys, let me show you, for example, we've really done this all along. Like if I was doing the derivative of 2x, or sorry, x squared, you really do the power rule. You bring down the 2, you subtract 1, you bring down the x, and then you do the derivative of this with respect to x, and that's 1. Like I'm showing you a chain rule. We really did it, but we didn't need to ever do it because it was the correct variable. So now when it's not the correct variable, we do the chain rule. To summarize, guys, this section, in one simple step, the only new thing, if it's the wrong variable, you put a dy dx next to it after you're done. That's the chain rule right here. That's pretty much the only new thing here. So now I'm going to solve, this is just y. This is the derivative. The derivative of y with respect to x. So now I'm going to solve for that. So I'm going to divide both, these are all multiplied, so I'm going to divide both sides by 2y. And that's it, but they really wanted it in terms of the x variable. dy dx, the derivative, is 1 over 2y. Well, what I can do is I can replace what y is. I solve for it over here, but doing a square root of y is really square root of x. And, oh, I forgot the 2. I'm sorry. There's a 2 there. And if we had done it this method, we would have gotten the same thing. The same thing. Okay, so as a recap, you do the power rule, bring the 2 down, subtract 1. I keep the y, but then chain rule says the derivative of this with respect to x, which is just the derivative of y with respect to x. We don't know it. If it was x squared, we would know it. The derivative of this with respect to x is 1. So you never need to do a dy dx when it's the correct variable. Okay, I'm going to do another example at the bottom, and then we'll talk about the general process for these. Any initial things, though, that I can answer before we look at another one?
But how do you go from 1 over 2y to...
I substituted. Like up here, doing a square root, I get y equals square root of x. And so I put that in right there for y.
So
Yes.
why wasn't, when you did chain rule, why wasn't it 1?
Because it was not the correct variable.
So if it would have been x, it would have been 1.
Yes. Yeah. So basically, if you see in these problems a y, and you're doing a derivative and it's of a y, then the chain rule every single time will just say dy dx after it. But if it was the x variable, it would say 1 after it. And so you don't need to do chain rule. Yes.
Why would you substitute in square root of x?
Just because this was in terms of a y variable. These are actually both, equivalent. This was in terms of the y. This was the answer in terms of the y variable. This was the answer in terms of the x. So I probably didn't actually have to on that one. They didn't say keep all values in terms of x, but I just kind of naturally did. Guys, good questions. Good questions. We'll do another one just so you see the process. And I want to show you where this would be helpful. So find the slope of this one. Slope, derivative, we'll plug in and get the slope. At the point 3, -4. What's this shape? Remember? Yes? Circle, yeah. So I avoided to now. Why would this, where would we need this, like implicitly, x's and y's together? A lot of the conic sections. I don't remember if you guys did much of the conics, but circle and some of the other ones. They're defined with x's and y's and together and squared. And so, yeah, basically what we're doing on this, here's a circle, 3, -4. We're getting the slope of that line, right, for the tangent line. Okay, so let me just rewrite it here so I have a little more room. You notice I leave a space there because I'm going to be writing derivative. So there's my function. Let's find the slope. I do the derivative. I really apply, just like I multiply every term by 3, I'm really applying the derivative of every single term. I'm doing the derivative of every term. Let me again just do the right side. Derivative of 25 is 0. Let's do this one. The derivative here is 2x, and it was the correct variable. Really, if you want to see my work, it's really this times the derivative of x with respect to x is 1. But we don't need a derivative with respect to x of x squared is 2x. This one, though, will need a little chain rule. It's basically, I guess, the same one as before, isn't it? The one above. Power rule, I bring down the 2. I subtract 1, y to the first. I bring down the y, and then I do, this is where I really need the chain rule, the derivative of this, the inside, is y prime, or dy dx. Again, I'm going to be saying this a lot. The general thing is just, all right, you did a y derivative, you write dy dx after it. So then we want the slope. Well, the slope will be the derivative functions. And so we're just going to solve for dy dx. So let's subtract 2x from both sides. I get 2y dy dx equals negative 2x. And then I divide both sides by 2y. And so the dy dx, this is my derivative. I can cancel a 2, and I get negative x over 1. So that's the derivative function for our circle that represents the slope at any point. Okay, now if it was the last question, just said find dy dx would be done, but they want the slope. So notice on this, remember what, like, we usually get derivative and just in terms of x's, right? We do something and it's got, I don't know, something like that. Then we plug in x. Well, we have x's and y's here. Fortunately, we have both an x and a y coordinate, 3 and negative 4. So, what was it? It was positive 3. So just plugging it in, and negative 4. And so this is my slope. Here, should I put my slope? 3/4. That's the slope, and yeah, makes sense too. It has to be positive here. Going up. Derivative this time, so x's and y's in there. Plug in your x and your y. Okay, let's flip the page. And any other questions now that we did that one? Okay, let's flip the page. Let me tell you this. I think I can do this page. I'm not going to hit. There's 2 extra problems on the following page that I'm not going to do. But I think I will be able to get these last 2 examples in here. Let me talk about so this is this summary of what you do on these problems. This is what I've been doing. You do step 1 says do d dx to both sides. Do the derivative on both sides to every term. You solve for, you get terms that have dy and dx on the same side. You will see that in this next example. You will need to factor it out, and you're basically solving for dy dx. That's what I'm just saying here. Okay. There might be multiple dy dx's, and so you just get them on one side and you factor, and you'll solve for this one. Okay, and that's pretty much it. So that's what I've been doing. Let me show you an example here, because this one's going to have multiple dy dx's in here. So find the tangent line. Tangent to this figure at the point -1, 2. Kind of the same question, but we'll just go ahead and get it to the full line. Anybody know what this shape is?
Is it a circle?
is not a circle.
How do you know?
I don't think I'll be able to go fully into that, but it's just
Just know.
well, circles are in the form, circles are in this form, r squared. And that was like the last one.
Were we supposed to learn that?
Oh yeah, and I'm not gonna really test you on knowing circle or all these, but I don't know, algebra 2 maybe?
It looks familiar.
We did a little in geometry, but I thought maybe algebra 2 was. No? Anybody have a guess for this one? Triangle.
Square. Trapezoid.
Rectangle.
Ellipse.
What's
Literally, how would I have guessed that? I don't even know what that is.
Okay, I know we did in geometry at least some with circles and ellipses. Do you remember at least doing that?
What's in
Isn't that a physical
Well, maybe they changed what you did a little bit in algebra 2. Well, anyways, an ellipse, otherwise an oval. Anyways, I'm not going to test you on knowing what shape it is. So an ellipse. Well, let's do the derivative. I think I'm just going to write it here, my first step here. I'm doing d dx to every term here. Okay, just so I save the step. So I'm doing step 1 from above. Differentiate both sides, with respect to x. Every one of those terms I'm doing the derivative of. First one, derivative of x squared with respect to x is 2x. Minus, the second one has an x and a y in it. It's x times y. So I have to do product rule. There's causing there, so you can do the thing. Product rule, right? Because it's two functions, x and y. It's not 3 times y. So I need to do a product rule. X is, so I'm parentheses here, because the minus is going to be distributed. So I got my x, my first term, my f. G prime, the derivative of y. Well, you do it as normal, right? Because x be 1, right? So if it's y, the derivative is also 1, but it was a y variable. And so then I'm really doing a chain rule. It's 1, then the derivative of y, which is dy dx. And again, I'm going to mention, if you're doing a y derivative, you're just going to write dy dx.
We have to write the 1.
Have to do it normally. No, you do not have to write the 1. I just put it there like I'm doing it like I'm just doing the normal derivative of x is 1. So I'm doing product rule plus the second one, my g, which is y. No dy dx. I didn't do it. I didn't do the derivative. I'm just writing it down. So I don't need the dy dx. Times the x, first derivative of x is 1. Okay, plus, so that was my product rule. Notice I put it in parentheses because I'm going to have to distribute the negative in a second. I'm on to the third one, the derivative of y squared. We've seen that a couple times already. This will be our third time. It's 2y, but I did a derivative with y, so it's dy dx. And then the derivative of 7 is 0. Let me distribute the negative. So I'm going to get rid of the 1 now. It's minus and then x dy dx. Plus, oh no, I'm sorry, it's a negative. Distributing the negative in. So minus y. Because it was y times 1, which is y. Now it's a negative y. Okay, let me rewrite this. Plus 2y dy dx equals 0. So on this one, notice there are 2 dy dx's. So that's why I'm on to step 2. I'm going to get all the dy dx terms on one side, everything else on the other side, factor, and then I'll get my dy dx. Yeah.
Where'd you get that 1 after the dy dx?
This one?
Yeah.
Oh, that was part of my plus. That was... I was starting to write plus, and then I was like, wait, take it back. I distributed the negative. So, thank you. I should get rid of that. So I'm going to keep these terms on this side, and I'm just going to write it here. Negative x dy dx plus the 2y dy dx. I'm going to get the other two terms on the other side. So really I'm subtracting 2x, and I'm adding y to both sides. So that was step 2. Collect the terms with dy dx on one side. Everything else on the other side. Step 3, factor out dy dx. This is how we get it by itself. I'm doing GCF right here, just a GCF. Of dy dx, I'll be left with negative x plus 2y. Over here it stays the same. And there you see, now we just have one dy dx term. That's our derivative, dy dx. Last step, solve for dy dx. Normally it's a division here to finish up. So I divide both sides by negative x plus 2y. And that's my derivative. I do just need to plug it in to get the slope. So let me just go ahead and finish it off real quick to get the slope. So now it's the same as the last one. I plug in my point, negative 1 for x, and 2 for y. So negative 2 times negative 1 is 2, plus 2, that'll be 4. Negative 1 times negative 1 is 1, plus 2 times 2 is 4, and that'll be 5. Should have it right. And why don't we just, I'll just write my final tangent line in point slope. I'm not gonna write it out. Y minus 2 equals my slope 4/5 x plus 1. If you do slope intercept, set it up, and I could distribute as well. I just want to make sure I get to the last one at least quickly here. So anything I can answer on that one? It was ellipse, didn't need to know that, but I wanted you to know now. It's ellipse. I do product rule and distribute the negative. Collect all the dy dx on one side by factoring out a GCF, and then dividing by the negative x plus 2y. And after that, you just plug in x and y like before. Yes?
So when you replace the dy dx for y, do you keep writing the y or not? Because like in the second line there, you kept the y for, the second line down one. Yeah, like you kept the y for the second part that you circled, but for the first circle you dropped the line just for dy dx. Do you see what I'm saying?
If you do a y derivative, you have to write dy dx. I don't see what you're saying. 1 times y?
Yeah, there.
Yeah.
Like it doesn't say negative xy dy dx. It just says negative x dy dx.
Yeah, okay, because I did, here, this was the derivative of y. So it was xy, so product rule was first. This was my f in the product rule. Then g prime, the derivative of y prime. So the derivative of y is this, it's 1. But with the chain rule, anytime you do a y derivative, it's dy dx. That's where it went. Yeah, so there was no y that carried down.
What's the difference between d dx and dy dx?
d dx says you're doing the derivative of something with respect to x. dy dx says it's the derivative of y. So if our function was z equals 2r plus 3, I would need to do dz dr, the derivative of z with respect to the r variable. So the first one tells you what you're doing the derivative of, and then the second one tells you the variable. And if it's just this, that says just the derivative of whatever it is, whatever you're doing. Good questions. No, just, well, let me see if I can set up the last one just to finish up. It is an equation. It says do the second derivative. So I'll set it up, and I might have to just finish up a minute tomorrow, but The first derivative is actually simpler than the last one. Second derivative, that's what that says here. Dx squared, and the d squared y, I know it's just weird that the squares are in different spots. Second derivative. So I'll do the first derivative of each of these as I've been doing. The derivative with respect to the variable x for each one. The first one is power rule, and it's 6x squared. The next one is also a power rule, but it's a y variable. So I do the normal, bring down the 2, it's 6. Keep the, so subtract 1 to the first power. Keep the y, that's my g, but it was a y variable, so really I'm doing chain rule now. And it's times dy dx. And then the right side is just 0. Okay, this is actually like one on the first page there. I'm solving for dy dx. I subtract the 6x squared. That's the next step. So I have negative 6y dy dx equals negative 6x squared. And for first derivative, last step is just divide by negative 6. Negative 6y, excuse me. So there's what we get. Dy dx equals x squared over y. Okay, I'm not going to have a lot of time for this, but I'll have to finish it tomorrow. But now for the second derivative, quotient rule. Okay, so I better stop there, but we will have the quotient rule. I'll just finish that up tomorrow, or really Monday. Just take a minute to finish that up. Quotient rule, and that's it. I think I do say write your final answer though, in terms of x and y. Yeah. Okay. Stop there. Okay, so finishing this one up, I would do the second derivative. I'm doing the derivative of each of these. The left side would be d squared y over dx squared. The right side, I do quotient rule. Low d high is 2x minus high x squared. D low, the derivative of y, is 1 dy dx. All over the low squared. That would be it. However, they say put your final answer in terms of x and y. This is not x and y. That's dy dx. That's a derivative. So, last step here. 2xy, I'll simplify that first one. Bottom is the same. Minus x squared. In place of dy dx, we know what it is. We just did it. Right here. I'm going to replace dy dx as a simple substitution. And it's x squared over y. You can leave it like that. There's actually many different ways to try and simplify that one, but we can leave it like that.